I want to show something like this. A binomial times another binomial. So let's take a look at x plus 2 times x plus 3. Now, if we were to kind of use the logic of what we just did, we could take this x plus 2 and consider it the thing on the outside. And we can multiply it by each of these things. That means we would have x plus 2 times x. And then we would have x plus 2 times positive 3. So positive 3 times x plus 2. So that's one distribution. But then we would have another level of distribution multiplying just the x times both terms. And then again, multiplying the positive 3 times both terms. And we would end up with x squared plus 2x, and then over here plus 3x, over here plus 6, positive 3 times positive 2. And then we could combine these center terms, 2x plus 3x is 5x. And we would get that this is x squared plus 5x plus 6. Multiplying two binomials together, and we end up with a trinomial as an answer, not another binomial. This is the idea of double distribution. When it's just a binomial times a binomial like this, there's a bit of a shortcut where we would multiply the x times both things, and then we would multiply the 2 times both things, because that's what we ended up doing anyway in the long run. And here, multiplying this x times this x, it's like multiplying the first terms together. And then this x times that 3, it's like multiplying the outside terms together, or the outer terms. And then we would multiply the 2 times the x. These are the inner terms. And then the 2 times the 3, these are the last terms. First, outer, inner, last. FOIL. First, outer, inner, last. FOIL. So when you talk about foiling, it can only be done when there's two binomials, and you could do the first, the outer, the inner, and the last. But notice you don't have to remember what FOIL means. You can just do double distribution. That's all it's saying to do. It's saying, hey, take this first thing and multiply it by everything, and then take this second thing and multiply it by everything. The first terms, x times x, is x squared. The outer terms, x times 3 is plus 3x. Inner terms, 2 times x plus 2x. Last terms, 2 times 3 plus 6, x squared plus 5x plus 6. More complicated example coming up. You don't even have to ask me once, let alone twice. Okay, here we have a binomial times a trinomial. 2x squared plus 4 times 3x squared minus x plus 5. It's not binomial times binomial anymore. So we can't just FOIL. We can't first, outer, inner, last. But we know what that process means. It means we take the first thing and multiply it by everything in the second. Take the second thing, everything in the second. So here we could take the 2x squared and multiply it by each of the 3 terms. We can take the positive 4, multiply it by each of the 3 terms. That'll give us 6 things added or subtracted together, depending on whether they were plus or minus, positive or negative. And then we combine our like terms and we'll get our answer. 2x squared times 3x squared. 2 times 3 is 6. We would have 6x to the 4th. X squared times x squared would be x to the 2 plus 2. Then the 2x squared times the middle. 2x squared times negative x. 2 times negative, that's going to be negative 2. X squared times x to the first would be x cubed. And then 2x squared times 5. 2 times 5 is positive 10. X squared, we don't have any x's here, so it's just the x squared we already had. Over here, 4 times 3x squared. We could just keep writing, plus 12x squared. Positive 4 times negative x minus 4x. Positive 4 times positive 5 plus 20. The only like terms we have are these. 10 plus 12. Positive 10 plus 12, that's positive 22. So 6x to the 4th minus 2x cubed plus 22x squared minus 4x plus 20. That's what we get when we multiply those together. Now, you don't have to write all 6 terms out in a straight line like this. Another thing you can do after one round through, the 2x times each of those 3 things, the 2x squared times each of those, When I came here and I did plus 4 times plus 3x squared, and I got positive 12x squared, I could have also lined that up. And then positive 4 times negative x, negative 4x, positive 4 times positive 5, positive 20. And then I could have added vertically. When we're multiplying and getting all of our middle step terms, you can line up the like terms so that you don't have to be looking everywhere to find where all your like terms are. You can line them up in advance, get the answer that way. Let's do another. Two y minus 1 times 3y squared minus 2y minus 1. So again, the reason that this double distribution even works is because it's like taking the entire 2y minus 1 and multiplying it by each. It's like taking the entire 2y minus 1 and multiplying that by each of them. And then each of those 3 has another 2. And that gives us our 6 terms overall. I'm saying, let's just get those 6 terms now. Let's not write out distribution twice. But if it helps you to think about it that way, show as many steps as you want. As many as you want. Here, I'm just going to go 2y times everything. 2y times 3y squared is 6y cubed. 2y times negative 2y is negative 4y squared. 2y times negative 1, negative 2y. Now I'm going to come here. Negative 1 times positive 3y squared. Negative times positive is negative 3y squared. And I'm going to line that up with the y squareds. Negative 1 times negative 2y. Negative times negative is positive. So plus 2y. Negative 1 times negative 1 is positive 1. Line them up. Add to combine our like terms. If you wrote them out, find your like terms, you're going to get the same answer. Negative 4 minus 3 is negative 7y squared. Negative 2y plus 2y cancel each other out. That's 0y. And then plus 1. Cancel each other out. It's like this whole thing goes away. 0 times y is 0. We get our answer of 6y cubed minus 7y squared plus 1. You would not leave plus 0y in the final answer. Okay. We have about 15 minutes left. Let's look at some special cases of multiplication in the time that's left. Let's say we have something in this form, a plus b times a minus b. What we're really looking at here is two terms added and those same two terms subtracted. This is going to result in something called a difference of squares. Difference because we're subtracting, of squares because we're subtracting two squares. Specifically, the first term squared minus the second term squared. These are called conjugates. Conjugates are what we have, and we have two terms, and we just change a plus in the middle to a minus in the middle. Conjugates. A-T-E-S. I know the E is in the light spot. The reason that it becomes a difference of squares when we multiply two conjugates let's think of foiling. First, a times a is a squared. Outer, a times negative b is negative ab. Inner, b times a, positive, that's plus ab, which is the same as plus ba, but when we have more than one variable, we like to keep it alphabetical. So we don't have to be thinking AB is the same as BA. We'll always see it with the A first if we write it alphabetical. And then positive B times negative B. Positive times negative is negative. B times B is B squared. Then a negative AB plus AB, those cancel each other out. And we're left with a squared minus b squared. So basically, we can do it the long way, but the middle terms cancel each other out. This is the only time that the binomial times the binomial will give us a binomial. You can't just multiply the a's and multiply the b's all the time. And it's always going to be a minus inside because those opposite terms make it a minus b squared. So how could we use something like this? Well, we could use it to skip the work. If we have 2x plus 5 times 2x minus 5, we could go the long way. 2x times 2x is 2x times 2x. Outer would be positive 2x times negative 5. That's negative 2x times 5. Inner, positive times positive is positive. Again, 2x times 5. And then last, positive times negative is negative 5 times 5. Now notice I haven't done any of the work here. 2x times 2x is 4x squared minus 10x plus 10x minus 25 minus 10x plus 10x cancel, and we get 4x squared minus 25. So we can do it the long way. No issue. Or we can notice we have conjugates. Two binomials. one with plus, one with minus, everything else the same. We can then set up a difference of squares right away by the formula. What are the two things that we're squaring? Well, the first and the second. And 2x squared, we use our exponent rule to get 2 squared x squared, or 4x squared, minus 5 squared, 25. So that's a difference of squares, multiplying conjugates together. Next, I want to talk about what happens when we square a binomial. Well, keep in mind that when we square something, it means multiply it times itself. So again, a binomial times a binomial, unless it's conjugates, it's not going to be just two terms. We would multiply the first. A times A is A squared. Outer, A times B plus AB. Inner, it's A times B again plus AB. Last, B times B plus B squared. Here, the middle terms don't cancel, but there's two of them. So A squared plus 2AB plus B squared. So we have this special formula. When we square a binomial, we can square the first, multiply 2 times the first times the second, and then square the second and get our three terms that way. If it was to be minus, so let's make this formula for plus or minus, what would that change? Well, it would be 2 minuses instead of 2 pluses. Wouldn't change A squared, but these would be 2 minuses. Negative times negative would still be always plus here. But AB plus AB is 2AB. Negative AB minus AB would be minus 2AB. So if there's a minus, if it's A minus B squared, that's going to make this a minus, but that one will always be plus. So we could do it the long way. There's nothing wrong with doing it the long way. If the formula confuses you, you don't have to use it. But if you did want to use it, it makes things quicker. You would square the first. And then whether it's plus or minus, that's what you would put here, whether it is plus or minus. Then you would do 2 times the first times the second, and then it's always plus, no matter if it's plus or minus. This second one is always plus. And then B squared, square the second. So if we had 3x minus 7 squared You could go the long way. You can say that means 3x minus 7 times itself. Under no circumstances should you say 9x squared minus 49, though. Because when you square a binomial, you're going to get 3 terms out of it. It means times itself. So you FOIL. First, 3x times 3x would be 9x squared. Outer, 3x times negative 7, negative 21x. Inner, negative 7 times positive 3x, negative 21x. Negative 7 times negative 7, positive 49. Combine your middle terms. 9x squared minus 42x plus 49. So the long way works. You can do the long way. Or you could use the special formula where we see that we're squaring a binomial, 2 terms squared. We square the first. We see if we have plus or minus. We go 2 times the first times the second. And then we go always plus. And then we square the second thing. Square the first, minus or plus. 2 times the first times the second. Always plus. Square the last. 3x squared is 9x squared. 2 times 3 is 6, times 7 is 42, minus 42x, plus 49. So you could use the formula and get there quicker. What are some ways that we can multiply 2 numbers together, 2 positive numbers, and get 12? 1 times 12. 2 times 6. 3 times 4. We already have 4 times 3. We already have 6 times 2. We already have 12 times 1. These are called factors of 12. They are numbers that you can multiply by other numbers in combination to get 12. Pairs of factors are specific pairs that multiply to 12. 1 and 12, 2 and 6, 3 and 4. This comes from the fact that, for instance, in the multiplication problem, 2 times 6 equals 12. 12 is called the product, and 2 and 6 are called factors. We deal with factors a lot when we're talking about reducing fractions. Recall that to reduce the fraction 16 over 24, one method we have is to create factor trees and find the prime factorization. In other words, breaking it down until all of the factors listed are prime numbers. So maybe 16 breaks up as 4 and 4. 4 breaks up as 2 and 2. And then in the end, we can say that 16 is 2 times 2 times 2 times 2. 24 could be 4 times 6. 4 is 2 times 2. 6 is 2 times 3. 24 is 2 times 2 times 2 times 3. So 16 over 24 can be rewritten as 2 times 2 times 2 times 2. 24 has 2 times 2 times 2 times 3. And then we can cancel pairs of 2's, and we're left with 2 over 3, 2/3. And that's one way to reduce fractions. Now, what actually canceled away here was one set of 2's, one set of 2's, and one set of 2's for 3 sets of 2's total. In fact, 1, 2, 3 sets of 2's are what we have in common to 16 and 24. 2 times 2 times 2 is 8. We call 8 the GCF, the greatest common factor of 16 and 24. Another way of finding greatest common factor of 16 and 24 would be to list all of the factors of 16, just like we did for 12. 1 and 16, 2 and 8, 4 and 4. For 24, 1 and 24, 2 and 12, 3 and 8, 4 and 6. 1, 2, 4, and 8. 1, 2, 4, and 8, they are common factors to 16 and 14, but what is the greatest common factor? What is the biggest number in both lists? 8, greatest common factor. We can extend this to variables. If we had x to the 5th and x cubed, x to the 5th is x times x times x times x times x. X cubed is x times x times x. What's in common? 1, 2, 3 pairs of x's. X times x times x is x cubed. So x cubed would be the GCF of x to the 5th and x cubed. In general, the rule we'll have is if we have the same variable, then the greatest common factor is going to be the lowest power shown. So for x to the 5th and x cubed, it's the same variable. The greatest common factor is going to be x to the lowest power shown. 3 and 5, what's the lower number between those two? 3. If we put these two things together, how to find greatest common factor of variables, lowest power shown. How to find greatest common factor of numbers, take the prime factorizations. Everything that's in common is a part of the greatest common factor. We could find greatest common factor of things like this. Let's find the greatest common factor of 12x to the 5th, 18x to the 4th, and 24x cubed. If we did a factor tree for the prime factorization of 12, 12 is 3 times 4. 4 is 2 times 2. 12 would be 2 times 2 times 3. 18. 2 times 9. 9 is 3 times 3. That means 18 is 2 times 3 times 3. 24. 4 times 6. 2 times 2. 2 times 3. 24 is 2 times 2 times 2 times 3. What's in common to everything? Well, we got some 2s. Looks like we got 3s. Nothing else in common to all 3 things, just a 2 and a 3. What about the variables? X to the 5th, X to the 4th, X cubed. They all have X's. The lowest power shown, 5, 4, and 3, is 3. 2 times 3 is 6, so 6X cubed would be the GCF of 12X to the 5th, 18X to the 4th, and 24X cubed. What we're going to do now is a process called factoring out the greatest common factor. First step, of course, would be to find the greatest common factor, which we just did. The problem we're going to look at, we're going to start with 12x to the 5th plus 18x to the 4th minus 24x cubed. Factoring out a GCF is basically doing the distributive property in reverse, backwards distributive property. So first we find the GCF of each term. 12x to the 5th, 18x to the 4th, 24x cubed, and we just found that. It was 6x cubed. By the way, the other way of finding the GCF of 12, 18, and 24 is make the lists. Find that 6 is the biggest number in all 3 lists. When the numbers are relatively small, you can do it that way, but as we start dealing with larger numbers, it's going to become easier just to do the prime factorization method every time. So I keep saying, I've said it a couple times now, distributive property backwards, distributive property in reverse. What does that mean? Well, this is 1, 2, 3 terms. So our leftover piece is also going to be 1, 2, 3 terms. 1, 2, 3. Hopefully now you're seeing distributive property in reverse. 6x cubed, what would go here to give us 12x to the 5th? 6x cubed times 2x squared would be 12x to the 5th. Now you're seeing why we did work with exponents, why we learned these rules. We need them to be able to factor. And just to check, 6x cubed times 2x squared, 12x to the 5th, yep. Next, 6x cubed times what is 18x to the 4th? Well, positive 6 times positive 3 gives us the positive 18. X cubed times x would give us x to the 4th. 6x cubed times what is negative 24x cubed? Well, Positive 6 times negative 4 gives us the 24. And we already have all of our x cubed. So let me bring that parenthesis in a little bit. And that is what we get when we factor out the greatest common factor. 6x cubed times the trinomial, 2x squared plus 3x minus 4. We can always check our work when we factor, because factoring is the reverse process of multiplication. That's why it was distributive property in reverse. If we multiply our factored form, we should get what we started with. And we do. (24) s cubed t squared plus 8 s t to the fourth minus 12 s to the fifth t. Let's factor out the greatest common factor. 24, 8, and 12. The greatest common factor would be 4. S is in all three of these. The lowest power shown is s to the first. T is in all of these. The lowest power shown is t to the first. So 4st would be the greatest common factor of 24s cubed t squared, 8st to the fourth, and 12s to the fifth t, or negative 12s to the fifth t. 1, 2, 3 pieces in the original. So 1, 2, 3 pieces in the leftover. 4 times what is 24? 4 times 6. S times what is s cubed? S squared. T times what is t squared? T. You can see why it has to be the lowest power shown, because we're going to be multiplying up to get to what we started with. And just check now, 4st times 6s squared t, 24s cubed t squared. 4 times what is positive 8? 4 times positive 2. S times what is s? We don't need any more s's. T times what is t to the fourth? T times t cubed. Just check, 4st times 2t cubed, positive 8s t to the fourth. We're good there. 4 times what is negative 12? 4 times negative 3. S times what is s to the fifth? S to the fourth. T times, we already have all the t's we need. So just checking, 4st times negative 3s to the fourth, negative 12s to the fifth t. That's our factored form. Looking in the leftover piece, there is nothing else that we can factor out. So this is completely factored. That means that is our final factored form. 3y times 2y minus 5 plus 2 times 2y minus 5. This looks completely different than what we were just doing. But there is a common factor. How many terms do we have here? It's only 2. This 3y times 2y minus 5, it's 2 things multiplied together. We are taking that and we are adding this thing, 2 times 2y minus 5. 1 term, 2 terms. What's the common factor? Well, we literally see it. The common factor here is this 2y minus 5. It is in common to both. It is the common factor. It is literally a factor in common to both terms. What do we do with it? We factor it out. Factor out the greatest common factor. There it is. When we factor out the greatest common factor, what do? The distributive property in reverse. We started with 2 terms, so our leftover piece is going to have 2 terms. Right, that's the dead one. Watch this. This times what is that times that? That times that is that times that. Literally, that times that is that times that. This times what is this times that? Literally, positive 2. This times that is this times that. Hope you see how we did the distributive property in reverse here. 2y minus 5 times what is 2y minus 5 times 3y? 3y. 2y minus 5 times what is 2y minus 5 times positive 2? Positive 2. So that's the factored form, the final answer, 2y minus 5 times 3y plus 2. Factored form is allowed to be written in either way. Why? Well, because a times b is the same as b times a. That's the name of the game. That was an ABBA joke. Okay. So we can switch the order. This could also be written as 3y plus 2 times 2y minus 5. These both mean the same thing. I'm going to do that same problem. I'm going to change it up a little bit. Move it in and make them X's so that we're sure that it's different. 3x times 2x minus 5 plus 2x minus 5. So last time we had 3y times 2y minus 5 plus 2y times 2y minus 5, or times 2. My point is, in the last problem, we had a number out here, like 2. We don't have a number here this time. So let me do this the same way. I'll use the same color coding. The common factor is 2x minus 5. So that's going to get factored out. 2 terms means 2 terms in the leftover piece. Two x minus 5 times what is 2x minus 5 times 3x? That's 3x. Now, 2x minus 5 times what is 2x minus 5? 2x minus 5 times 1. Not just any kind of 1. Positive 1. 2x minus 5 times 1 is 2x minus 5. We can imagine that when we have plus this thing in parentheses, we have plus how many? Plus 1 of these things in parentheses. If we write in the imaginary 1, then to get this leftover piece, we could just do 3x plus 1. 3x plus 1. And we get that as the answer. Let's do another like that. I'm going to stop the color coding. (5w times w minus 3) minus, in parentheses, w minus 3. The common factor is w minus 3. We take that out. We have our imaginary 1, 5w minus 1. That's it. Doing all that color coding was just making it more complicated in terms of what I'm writing. But the common factor gets factored out, and then what's left over is right there. This is going to be the basis of something called factoring by grouping. So today we're looking at greatest common factor and factoring by grouping. Before we get fully into the factoring by grouping, let's look at a very specific direction, and then we'll move on. Factor out -4 from the polynomial -4x squared minus 8x plus 12. Here we are specifically told to factor out a -4. That means we don't have to worry about looking for the GCF or anything like that. We're just told, hey, factor out a -4. So if a -4 is coming out, we need to think about the distributive property in reverse to find out what the 3 terms in our leftover piece will be. 3 terms in the leftover piece because 1, 2, 3 terms in the original. Negative 4 times x squared is negative 4x squared. Negative 4 times positive 2x is negative 8x. And negative 4 times positive 3. No, not positive 3. Negative times negative is positive. So negative 4 times negative 3 is positive 12. All we're doing is thinking about the distributive property. What would we have to get us what we're starting with? Factoring out a negative 4 means a negative 4 is on the outside. We imagine what would we have to be distributing through to get us what we're starting with.